Thank you, Karl-Heinz, and thank you, everyone. Hope you're having as much fun here as I've been having the last couple days. So this is unusual for me. I'm a neuroscientist. I always pride myself in giving one of the most neuroscience-heavy talks at NICE. Today, you're going to see no brain inspiration at all, other than my tie. What I want to talk about instead is a problem that is particularly relevant to Sandia as a national laboratory and DOE labs in general as we go forward into where I think a lot of people are appreciating are the limits of high-performance computing, pushing exascale, trying to get past the sort of energy boundaries. DOE labs are often concerned with giant physical simulations, really big climate models, for instance. And as these get more and more sophisticated, the power budget required to run these is starting to become the limiting factor. We talked about that this morning with the end of Denard scaling a number of years ago, and this is really beginning to hit home for Sandia and other labs. So just as an illustration of this, if you look at the top 500 supercomputers, the list that came out a few months ago, we're not even close to exascale quite yet. We're still in the tens of petaflops range, and we're already getting close to dozens of megawatts to run these supercomputers. And if you look at exascale, we're looking at things that are going to get close to 100 megawatts. There are a lot of countries in the world that do not have 100 megawatts of power capacity. So we're talking about supercomputers that are really going to be limited by where you can put them by what the power supply is. And so the question is, for a community like NICE, if we have low power hardware, is there something that we can do with some of these chips, some of them make-believe, some of them real, and stick them onto a supercomputer blade? This, I believe, is the Oak Ridge blade that was just talked about a few minutes ago, and have a hybrid architecture that includes not just CPUs and GPUs, but also a neuromorphic processor. So there are obvious things you might do with this. The obvious one is going to be machine learning, what we just heard about. We have an exascale machine. We want to have in situ analysis of our simulations. That saves on a lot of computation time, especially post-processing. And of course, a lot of people are going down this path. There's a lot of opportunity there. There are other things you can do as well. One is you actually just model neural computation, something more cognitive. Spinnaker, in a lot of ways, Spinnaker is a supercomputer to do biologically inspired neural simulations. I'm going to talk about something a lot more, I believe, controversial, and that is, can you actually get the neural chips, spiking neural hardware, to do numerical scientific computing in the classic applications that people build HPC for? So can neural computing compete on something that is dominated by CPUs and related technologies? So the reason this, I don't think, is a crazy thing to start is that if you think about what these neural chips are, they're chips with hundreds of thousands, maybe millions of very powerful logic gates. The McCulloch-Pitts neuron is just a more powerful logic gate than a classic, simple and/or not sort of gate. And if you build off that, you can actually do any sort of math that we do with conventional logic gates, which is anything. We can do that with neurons. And spiking neurons are just an extension of McCulloch-Pitts neurons. So there's no fundamental reason that neurons are incompatible with conventional logic. So we've actually explored this over the last few years. We've had a couple of posters here at NICE, I think last year and the year before. You heard Craig Vineyard talk about sorting algorithms and spiking hardware. We've done cross correlations. We've done matrix multiplication and spikes. So all these things, they have some advantages, they have some limitations. So we wanted to actually push this a little bit further. This is a new project, something that we're only 6 or 7 months into right now. So kind of like Wolfgang earlier, this is effectively the first time I've talked about this work in the public. So bear with me on this. But so the idea is let's look at diffusion. This is a partial differential equation. It's very, very simple partial differential equation. And in the simplest case, it's analytically solvable. But it underlies many physical processes that are relevant broadly in terms of computing. I have a couple of examples here. These are diffusion processes that are effectively Brownian motion, sort of random walks. The diffusion equation is modeling what a population of random walkers do. There's a fundamental equivalence between many random walkers experiencing Brownian motion and the diffusion equation as written above. So these three cases, one of these is a stock price. One of these is solar flare events. And one of these is a win-loss percentage of a baseball team. This is a generic process that underlies many different computations one may care about. So the question is, can we model random walks with neurons? And can we do it efficiently in such a way that opens up neural computing to a whole new application area? So there's a reason we pick random walks. It's very simple. I mean, obviously, you have a particle, it's at a position, it can either move left or right in a one-dimensional case, or maybe not move at all. You can approximate the PDE solution if you have many particles, but you need a lot of particles to do that. And so there are a number of cases where we use this in scientific simulation as opposed to the more conventional deterministic solutions, particularly high-dimensional diffusion equations, things like Boltzmann equation and so forth. We might want to actually simulate many random walkers, and people do this today on high-performance computing platforms. So the reason I might work with neurons is that the math is simple, and it's an embarrassingly parallel sort of thing. So I can build a lot of walkers and just let them go. And they don't really need to communicate with one another if I'm modeling a system where you don't have interaction of the particles. So if I can manage to make a random walk circuit that has relatively few number of neurons and scales well in the space and the number of particles I care about, it might be an opportunity for neural computing to have a win. So we have a little circuit, and we're looking for just these things, like how many neurons, how many connections, what the sparsity is of the representation, how much energy is required to update those particles over time, and so forth. So there's some obvious things you can do with neurons and representing particles. So ultimately, we have to represent space. If I have a particle moving around, moving left and right, simple, but there are a number of, any location I want to cover, I'm going to have some spatial representation. So I could have a binary representation. I have a population of neurons. These are spiking, so they have to kind of maintain an activity. I lose my power advantage if I use a binary code because my expectation is half the neurons are going to be active for any given location I'm at. It's also not going to be easy to update. You have place value, which means that I'm going to need to have a fairly sophisticated neural circuit, at least compared to the representation, to update that value. The alternative, or the other naive alternative, is a unary code where my 30 positions are represented by 30 individual neurons. This is obviously not going to be scalable. But it's incredibly easy to update. I just have, if I want to push that neuron to the left or right, I just push it to the left or right. This is equivalent to, say, a place field code in the hippocampus, where position is located by a neuron in that location. So we thought about this, and we actually did something which is analogous to things that people used in the pre-radio days of locating position. So we want to locate the position of a moving object. Well, ships had to deal with this in finding longitude. You can look at how high the sun gets at noon to identify latitude, but longitude was a hard problem. The solution that was developed mostly by the British Empire, but other countries as well, was to compare a clock, say a really sophisticated chronometer that's on the ship, and the time of that clock relative to the time that you see the sun or the moon reach a certain position relative to what you would expect to be in London. So this sort of comparing a reference clock, which is kind of a global Greenwich time, to the clock you have on your ship, allowed you to compute kind of a difference between your two clocks, and that told you where you were on Earth. So we did something similar to this. We built little clocks out of our neurons. Instead of a long clock that had, all the time represented in one ring, we actually used a series of ring oscillators. You can have any number of them. But if they're prime number lengths, the sort of representational capacity of these circuits is the product of those prime numbers. So in this case, your rings of 5, 7, and 11 yield almost 400 possible states that can be represented. And so as each of these is kind of moving forward, every time step, each ring shifts forward by 1, you'll eventually repeat yourself only 385 time steps in the future. And you'll have unique codes all the way up until then. This is not a novel code. It's kind of well understood mathematically. But what we decided to use it is we have a reference code, so kind of a fixed state. So in other words, the sort of origin, so to speak, of my system is always moving forward in time according to this clock. And each of my particles has its own independent circuit, and it itself moves forward in time according to its own clock. But if I want to advance that particle, if I want to move that particle to the right or move it to the left, all I need to do is shift the particle's rings forward by 1 or back by 1. Shifting the rings turned out to not be all that complicated. All the obvious things you might try don't work perfectly, but with a few little tweaks, you can get it to work pretty nicely. So you have a constant number. You never need more than 10 neurons additional to the ring neurons to allow to update the rings forward or back. And if you want to have multiple dimensions, you want 2 dimensions or 3 dimensions, you just have a different set of rings for each dimension you care about. So this thing here scales really well. When we do the math, it's not quite binary code efficient, but it updates a lot more similar to a unary code, so we kind of land in the best of both worlds. If you have a lot of rings, so if I want to get closer to a binary code, I can get by with many small rings, but I have to pay for that in terms of energy. Alternatively, if I want to have a small number of rings, that means I only need a handful of spikes to represent the location or any update at any given time. But that's going to require more neurons. So these equations probably don't mean that much, so I ran out a few examples. If I want to represent 1,000 spatial locations in a particle, I can get by with, say, a set of the sizes 7, 11, and 13. That gives me 1,001 possible locations, and that only requires about 60 neurons per walker. So if I have a board or a chip that might have 500,000 neurons, I'm going to be getting close to maybe the potential to have 10,000 walkers running in, with the precision of 1,000 locations. So that's a lot of walkers. If you consider that if I want to have walkers running in parallel on a supercomputer, I'm going to still need at least 1 core per walker in order to get fully parallel implementation, unless I want to serialize those walkers within the cores. So we can get a lot of walkers onto a single neuromorphic chip this way. If you do 2 dimensions, you get a lot of possible locations. You require twice as many neurons, but you get a lot of potential locations out of that. If you want to get 10,000 locations within 1 dimension, you double the number of neurons, you go from 1,000 to 10,000 locations. So it's not exponential scaling, but it's a lot better than linear scaling. So this works. We did some simulations of this, and you let the walkers go. They diffuse. They do what they're supposed to do. You compare this to just kind of a direct simulation. You get the same results. We're taking advantage of stochastic properties in these chips, where the ideal is each walker is going to have some random number generators to move it back and forth. Not everything is random, but we're going to take advantage of the presence of many little random, say like a random threshold neuron to start it. These things are really a torus because it's just orbiting. So just if you go beyond the capacity, you're just really flipping on the other side of that torus. So that's the basic random walker code that we came up with. And we think this has potential to be applicable for a number of these areas. But then we were thinking, if we're going to be thinking about these neuromorphic processors as kind of giant parallel supercomputers with lots of configurable neurons, can we actually model the mesh itself and do the stochastic processing at each vertex of the mesh as opposed to a walker moving along the mesh? So this is, in a sense, we want to have a circuit now at each of these positions as opposed to each of the walkers moving along a position. Looks something like this, where now I repeat this little circuit. I'll explain it more in a second. And you repeat that circuit on every location. Now, at first glance, this looks like it's not going to be nearly as efficient. But there are cases where you might want to do this. So the first thing is that this method is actually independent of the number of walkers. If I have time to wait, I can have as many walkers in this system as my model requires me to have for whatever boundary conditions I care about and so forth. It's the precision of my walker counter is just going to be counting down the number of walkers. Each walker, the circuit kind of passes on the walkers either to whatever neighbor the coin flip says it should go to, or it keeps it locally. And there's a little small circuit, moves some things around like that. So I don't pay for the number of walkers. I can just, if I want more walkers, I basically just have a longer simulation. That's really nice compared to the way, you need a lot of walkers for these stochastic processes to work. This is an illustration of what the density method looks like. So these, you see this checkerboarding effect just because the way the probabilities in this, it's either going left or right, doesn't stay in the same place. But it diffuses the way you would expect. Pardon me. So this is what a one-dimensional case looks like over time. And this point here, it's mixing. This is an interesting feature of this process. As I say, you pay for it in time, and the time it takes to move forward a time step is dependent on how many walkers are in the densest position. So in a sense, since each time step you're going to serially go through every walker located, you have to wait for the densest position to go through everything and let go of it. But as the thing mixes, as you move from left to right on that diffusion plot, you get much shorter time steps. And the model effectively, the wall clock time speeds up in a sense. So this is actually the spike raster plot of what you see on the left. In this model, boundary conditions are almost trivial to implement. It's what you just have is a graph where you're diffusing over that graph. You have a boundary. You just don't have an edge between the vertices where you want to go. It's a boundary, it just doesn't go past that. It doesn't go through that green wall, for instance. The graphs on this case don't have to be a 3D Euclidean sort of mesh. They could be any graph you want. If I want to model a social network, I can just build a social network with a bunch of density of walkers and watch how information diffuses through that network, which may have nothing close to a spatial structure at all. So this is just the diffusion, the density process that we discussed, kind of laid out on one slide. The nice thing about this density method is that at any instant, I can take a snapshot of what the whole density profile looks like. I don't have to integrate over all the walkers. I don't have to consolidate that information and say, at time 20, where were all my walkers at that time, and do post-processing. In this case, I just go at time 20 and I say, give me a readout. Where am I? So anyway, those are the two methods that we've looked at. We are beginning to implement this on the Spinnaker platform in particular, but we're looking at other neuromorphic platforms. I think all of them have pros and cons. These are fairly compact circuits. They're sparsely connected, so they should be pretty easily fit on many of these things. In terms of these two methods themselves, there are times at which I imagine that one is going to be more useful than the other. The random walkers, I get path-dependent behavior. If I'm tracking stock prices, for instance, if I have a path-dependent financial option where it's not just the endpoint that matters, but rather the path through which the stock goes that determines the value, I actually need to have each of those paths available at any given time for me to assess that value. Alternatively, if I'm looking at a diffusion process for solving a PDE, maybe all I care about is the density, which is ultimately what that kind of partial differential equation is really modeling, is the densities over time. And so in that case, the density method itself might be more useful. So we have these two methods that have different cost benefits. and that we're really beginning to explore at the moment. So in conclusion, we have evidence now that spiking neural hardware, the stuff that you all are developing, is actually not just suitable for things like numerical computing, but in some cases, like random walks, may actually be advantageous. And like I said, this is early in the exploration of the process. We haven't mapped it to any real-world problems yet, but at least at a core theoretical level, there's a lot of potential here. These are the particle method is a constant time method. It's very fast, should be readily scalable. And the density method, I think, actually has broad applications beyond just looking at diffusion in a physical space, but actually in more abstract situations. So I want to acknowledge people on my team, William Severa, who did the videos that are fancy. He'll be talking tomorrow about a different project. And thank you very much for your attention.
Thank you, Brad. There's a question there and there, yes?
Okay, sure. Go ahead.
Thank you, Brad. Are we looking at the emergence of so-called design patterns for neuromorphic computing?
So how do you mean?
Yeah, in the sense that, like a design pattern in a traditional software engineering sense, that you could look at a particular problem and have a sort of a library of methodologies in order to solve that problem, higher abstracted methodologies. Like if you have a problem that can be well simulated by random walks, then these are sort of patterns that you can use as a sort of a higher level abstraction.
Yeah, so that's kind of, if I follow you, that's where we're trying to get to, is if we can build sort of core computational kernels, whether it's a convolution or a random walk process, and do it in a compact number of neurons, then we kind of move up from the spiking neuron level of abstraction and go to something that's more familiar and useful to people who are mainstream computer scientists. I mean, and I sit in a national lab where most people are computer scientists and never want to think about a neuron, much less a spiking neuron. So that's very much what our direction is. We're trying to bring this technology to something they could use.
Do you have any, it's a great talk, do you have any rough sense of the power consumption, power equivalence to a classical architecture for the same thing?
So we're going to do our homework very directly on this. The intent was for this to be a low power process. And if you count spikes as your surrogate of power, which at least as a first order approximation is not a bad place to start, these are pretty spike efficient. So there's, you don't need very many spikes for the random walkers to exist. That's one reason we didn't do a binary code, for instance. But we want to go through and be fair about an apples to apples comparison with conventional implementations. So I know for a fact that if you go and say, well, this is a great method, it's going to be fantastic, and someone says, well, we can do something similar on CPUs and do it low power if that's what we care about. So we want to make sure that there's something fundamental here. So I don't want to promise that we're low power, but we think that there's a lot of potential for that.
It's also reminiscent of cellular automata at some
It does have similarities to that. And I think random walks and cellular automata are related in a lot of ways. That wasn't sort of the driving, we're really focused on this diffusion sort of process as opposed to something a little bit more intelligent, so to speak.
So if I remember well, the Fita code had some overhead in encoding and decoding. And so what would that mean in terms of interacting particles, which is, I guess, also interesting from particle multi-color?
I was hoping no one would ask me about encoding and decoding. So the encoding's easy. I mean, you just set up your simulator, your walkers, they're all at the origin, it has a certain position. For decoding, what you're going to have to do is you're going to compare the compare these walker, these sort of rings. That's fine. So those two sets of rings, the top one's my reference and the bottom one's my position. I'm going to have some circuit that compares. We think that's going to be fairly straightforward, but we have not designed that yet. I will say that one other benefit is my reference does not have to be a fixed point. I could actually reference to any other particle. So I just compare, I do a modular difference between the two sets of kind of the residuals between the two sets of codes, and I can get that difference. But we have to build a circuit for that, and there will be a cost associated with it. Now, that might be something we can learn. It might be something we hard code. It may be fairly trivial, but I don't want to promise that.
Okay, thanks, Brett.
Thank you.